In this course, we're going to take our very first steps into the world of Cobol programming, a language that still powers a large part of the banking and insurance industries today. But we won't stop at just learning Cobol. This course also gives you hands-on access to a mainframe environment, just like the ones used in production systems. Here's what you'll learn. First, we'll explore the mainframe interface. You'll get comfortable using TSO and ISPF, understanding how the file system works, and monitoring jobs through SDSF. Then, we'll dive into the basics of Cobol development. You'll write your first program, learn how to compile and run it, and understand the structure of a Cobol application. Throughout the course, you'll find practical exercises designed to help you practice and build confidence step by step. Let's not wait any longer, and let's begin by setting up your development environment. It's very important to me that you get the chance to put into practice everything you'll learn in this course. Because real progress comes not just from watching lessons, but from getting hands-on experience. That's why I'm giving you 1 week of free access to my personal mainframe server as part of this free course. To take advantage of this offer, simply go to my website, coboltraining.com, and visit the Mainframe Access page. There, you'll find a short form to request your access. Once completed, you'll receive an email with your TSO user ID and the IP address of the server, so you can start practicing directly in a real mainframe environment. This is a great opportunity to get comfortable with TSO, ISPF, and Cobol in the same environment used by companies around the world. So don't wait, go ahead and claim your access now. Let's start by downloading the Quick 3270 terminal, for which I'm providing you with a license as part of this training. A terminal is a tool that allows you to interact with a mainframe. There are several available on the web. To download it, go to the website dncomputing.com. On the homepage, navigate to the Downloads section. Then choose the 64-bit version of Quick 3270. I won't go over the installation process on my end, since I've already done it. Once installed, open Quick 3270. The free version of Quick 3270 is available for 2 months. For those taking the paid version of this course, you've received a premium license by email. We'll start by activating this license. For those following the free version of the course, don't worry. The 2-month trial period is more than enough to complete the course. We'll begin by activating the license. To do this, go to the Help tab, then click on Enter License Key, and paste the license key you received by email. We will then configure the terminal to connect to the mainframe. To do this, go to the Session tab, then Session Configuration. In the country field, select Latin 1 and enter the host and port values provided in the email. To connect to the mainframe, go to the Session tab, then click on Connect, and you should see the ZOS login screen appear. To log out, click on Disconnect. Finally, save your session to preserve this configuration. You will use this session file to connect to the mainframe later. Now, let's see how to connect to the mainframe by logging into your TSO session. At this point, you should see the ZOS login screen on your display. To log into your session, type the command logon followed by your TSO user ID. For example, if your user ID is user01, you would enter logon user01. The cursor must be placed on the line where you're supposed to type the command. Normally, it's already positioned correctly when you reach this screen. However, if it's not, for example, if you clicked somewhere and the cursor moved, you can use the Tab key to reposition it to the expected location. Then press Enter. TSO will then ask for your password in the password field. Enter it, and before pressing Enter again, make sure that the other fields contain the same information as shown on my screen. Then press Enter. When you see ISPF, press Enter once more. You'll now arrive at the main ISPF screen, which we will go over next. To log off from the system, simply go back step by step using the F3 key until you reach this screen. Before logging you off, the system asks what you want to do with the SPF log file. This is a trace file that records certain activities from your session. It is not necessary to keep it. Select option 2 to delete the trace file and press Enter. The command ready will appear, indicating that the system is waiting for a command. Type the command log off to disconnect from the session. After a few seconds, the ZOS login screen will reappear. You are now successfully logged off. If you reach the ready screen by mistake, for example, if you pressed F3 too many times, but don't actually want to log off, simply type ISPF to return to the main screen. Let's now look at how to navigate within this system. Everything is done using the keyboard. You have a white cursor indicating your current position. At the top of the screen, there is an option line where you can type your commands. For example, to access the Utilities menu, type option 3 and press Enter. To go back to the previous screen, use the F3 key. To move from one field to another, use the Tab key. You can also use the arrow keys to move the cursor around, or even use the mouse to quickly position the cursor, make selections, and perform copy and paste actions. There is also a very useful command called Start, which allows you to open a new screen. You can have up to 8 screens open at the same time. Managing multiple screens is made possible by the Swap Bar option, which is enabled by default in your session. The different open screens are represented by white labels at the bottom of your screen. To switch between screens, simply place the cursor on a label and press Enter. You may notice an asterisk and a dash in front of some of these labels. The asterisk indicates the current screen you're on. The dash indicates the previous screen. You can quickly return to the previous screen with the F9 key, which corresponds to the swap function. We also have what are called PF keys, which mean program function keys, like F1, F2, F3, and etc. We've already seen that F3 is used to go back. These PF keys are often displayed at the bottom of the screen. Here's a quick overview. F1 is used to display help related to the current screen. F2 is used to split the screen in two. This is the split function. To use it, place the cursor where you want the split to occur and press F2. This is useful, for example, when comparing data between two screens. To cancel the split, place the cursor at the top of the screen and press F2 again. Sometimes the screen may freeze, for example, if you try to type something while the cursor is not in a valid input field. In that case, you'll see a special symbol appear in the bottom left of the screen. To unfreeze the screen, simply press the Control key. There are other PF keys, but we will explore them later in the course. Let's now take a closer look at the ISPF menus. We'll just explain what the menus are for now, and we'll explore them in more detail later in the course. The first is the Settings menu. This one is self-explanatory. It's the menu where you can customize your session based on your preferences. A slash in front of an option means that the option is enabled. You can define settings such as the position of the command line, the functions assigned to function keys, and the screen colors. Then we have the View menu. It allows to display files. When I say files, this can include plain data files, programs, configuration files, and so on. On option 2, we have the Edit menu, which is used to modify files. Personally, I don't use the View and Edit menus because everything can be done from the Utilities menu on option 3. In fact, most components we'll be working with are files, and all file-related actions are grouped under Menu 3. It contains several submenus. Here are the ones we'll be using most. Dataset is used to manage files, meaning create, delete, and rename files. Move copy is used to copy files. DS list is the most frequently used. It lets you browse and edit files. Super C means super compare. It is a module for comparing files. And search for is used to search for a string within a file. To quickly access these sub-menus from the main ISPF screen, you don't have to go step by step, like typing 3 then 4. To access DS list, you can directly type 3.4 from the main screen. If we go back to the main menu, we have then the DITO tool. It is used to work with some file types, such as VSAM files, which can't be directly viewed or edited from the Utilities menu. In this case, we use DITO to display and edit them. Then we have SDSF. This is the System Log and Report Manager. It's where you'll find output reports from your programs after compilation and execution. This menu is essential for identifying syntax errors, bugs, and other runtime issues. On option 12, we have XDF. It is a tool that makes accessing files easier. You can create shortcuts by assigning a number to a file. For example, the file user01.dev.cobol has been linked to option 1. You simply type 1 in the number field to open it. And finally, we have the Database menu. This is where you perform database-related actions. We'll see later in the course how to create tables, insert data, query them, and more. Before developing our first Cobol program, we'll first take a look at the file system. In ZOS, there are 2 main types of data files: physical sequential files, known as PS files, and partitioned datasets, known as PDS. To better understand the difference between the two, we can compare them to elements you're already familiar with in a traditional file system. A PS file is similar to a regular file. A PDS is more like a folder containing multiple files. A PS file is a single file made up of records stored sequentially. This means that the data is read or written in the order it is stored. A PDS, on the other hand, is a file that contains multiple members. Each member acts like an individual file, and the set of all members forms the PDS. They can also be called libraries. It is commonly used to store programs, scripts, or configuration files. So you can think of a PDS as a folder that contains several files. Now let's see how this looks in ZOS. In ISPF, you access files through the DS list menu. So you go to option 3, then option 4, or simply type 3.4 from the main screen. To browse files, enter the file name on the DS name level line and press Enter. I have already defined files for each user, and they are prefixed with the user's ID. For example, since my user is user01, I type that ID and press Enter. The list of all files starting with user01 will appear. To perform an action on a file, type a command in front of its name. For example, to view the content, you can type B for browse or V for view. With both options, you can't modify the file. To modify it, use E for edit. You can also place a slash in front of the file to display a list of available commands. These include the ones we just mentioned, like browse, view, and edit, as well as delete, copy, and etc. Let's take the example of the file user01.spoofy.in. This is a PS file, so a sequential file. I open it using the View option. This brings us to the file editor. Here's what it looks like. You'll see the line numbers on the left and the data in the center. You can type commands on the top command line. For instance, the command ":on" displays the column numbers. We'll take a closer look at the file editor in the next lesson. I exit the file using the F3 key. Now let's view a PDS. For example, let's look at user01.dev.cobol. I created this to store my Cobol programs. There are two programs in this library, CICPGM1 and CobDB01. And you can perform actions on these members the same way as before, so I enter V in front of a program to read it. In the next lesson, we'll learn how to edit a file. In this lesson, we will learn how to modify a file, which is a prerequisite for writing Cobol programs, since those are also files. To do this, we'll go to Menu 3.4. You already have a pre-created PS file available named user01.file. To edit it, type the command E in front of it and press Enter. We'll start by inserting a line. To do this, position your cursor on the first line of asterisks. Type the letter I and press Enter. You can then enter some data. Press Enter again to confirm the input. This will insert a new line. If you confirm again without entering any data, then the second line won't be inserted. You'll notice that line numbers are displayed when you create new lines. We can manage file lines by typing commands directly on the line numbers on the left-hand side of the screen. Let's look at a few useful commands. To repeat a line, use the letter R. To delete a line, use the letter D. To copy a line, use the letter C. You must also specify where to place the line using letter A or B. A stands for after, B for before. For example, type C in front of a line to copy, then place A on line 1 to paste it after line 1. Or place B on line 2 to paste it before line 2. To move a line, use the letter M, and again, use letter A or B to specify the new location. You can also perform block operations. For example, to delete a block of lines, type DD on the first and last lines of the block. The same logic applies for copying and moving blocks, just don't forget to use A and B. Finally, you can perform repetitive actions by adding a number after the command. For example, I10 will insert 10 lines. D3 will delete 3 lines. We can also type commands in the command line at the top of the screen. Here are a few of those commands. :on displays column numbers. Save saves the file. If you exit with the F3 key, the file is saved automatically. Cancel exits the file without saving. You can also use the F12 key to exit without saving changes. Now, let's see how to handle screen overflow and how to navigate through the file. To show you this, I'll add 60 lines so that the content exceeds the screen size. Also, I'll fill the first line entirely to show column overflow. The visible columns on the screen go from column 1 to column 72. The F11 key allows you to scroll right. When I scroll, I can see that the file is defined with 80 columns. Most of the time, sequential files have a fixed length, meaning each line is the same length. It is also possible to create files with variable length records, but we'll explore that later in the course. Cobol programs themselves are files with a fixed length of 80 characters. To navigate vertically through the file, use F8 to scroll down, use F7 to scroll up. To navigate horizontally through the file, use F11 to scroll right, use F10 to scroll left. At the top right, there is a scroll option that can be set to page or cursor. Simply type P or C to choose the scrolling mode. In cursor mode, when using F7 and F8 or F10 and F11, the screen will refresh with the line or column where the cursor is currently located as the first one displayed. For example, if I place the cursor on line 10 and press F8, line 10 becomes the first visible line. Same for columns. If I place the cursor on column 2 and press F11, column 2 becomes the first visible column. In page mode, cursor position is ignored. The display scrolls by one page, meaning the next first line or column is simply the next in sequence. So now you know the main commands to edit a file. What I've shown here isn't exhaustive. We'll look at more commands later in the course. But you now know the basic editing commands needed to write your first Cobol program. We're now going to code our first Cobol program. It will be a Hello World program, which is a classic when starting out in programming. The goal of this program is to display the message Hello World in the output console. First, we'll create the file where the program will be written. To do this, we go to option 3.4. I've already created the libraries that will contain our various development components. We'll store our Cobol programs in the PDS named dev.cobol. Cobol programs are written in files where each line can have a maximum of 80 characters, just like on the original punched cards. In DSList, the command I allows you to view the characteristics of a file. Indeed, we can see in the record length attribute that the PDS has a length of 80 characters. But don't worry, we'll see later in the course how to create files and define all their attributes. We'll now create a new member in this library for our Hello World program. Make sure to use the library corresponding to your user. To do this, type E in front of the library name in the command column and add the name of the new member in parentheses right after the library name. We'll name the member Hello. First of all, you should know that a Cobol program is read from top to bottom, and you can't write things just anywhere. Let's type the command cols_on to display the column numbers. The structure of each line is very strict, with well-defined zones. Columns 1 to 6 were traditionally used for line numbers. These numbers were useful in the era of punched cards to restore the correct order if the cards were shuffled. Today, they are no longer necessary, and you can write whatever you want in them. Column 7 has a special role. It serves as a line type indicator. For example, an asterisk indicates that the line is a comment line and is therefore ignored by the compiler. Columns 8 to 72 is the actual Cobol code area. Finally, columns 73 to 80 are ignored by the compiler. They were often used for sequence numbers. This format is essential in mainframe environments like ZOS and even in some specialized code editors. To insert a line, type the letter I in the first starred line on the left and press Enter. A program is divided into 4 divisions. The first is the identification division, declared starting at column 8. This division contains general information about the program. This is where we declare the program's name using the program ID instruction, and we'll name our program Hello. Next is the environment division, which declares input and output files for the program. Since we don't have any files to manage in this case, we'll leave this section empty. The third division is the data division, where we declare our variables. Finally, we have the procedure division. which contains the logical code of the program written as instructions. For our first program, we'll simply write two instructions starting at column 12. The first is display hello world. The display instruction outputs the string that follows it to the console. This can be a variable or a hard-coded string, as we've done here. The second instruction is stop run. This instruction ends the program. We can also enable syntax highlighting with the command hi Cobol. And that's it. We've written our first program. Now let's compile it. For our program to be understood by the system, it needs to be compiled. Compilation is the process of transforming a program written in a given language into a binary file. Compilation is done using a job called a JCL. JCL stands for Job Control Language. It is a script used in mainframe environments that allows you to execute tasks, such as running Cobol programs, and it specifically enables Cobol program compilation by defining the necessary resources and instructions. Here's what happens schematically. The Cobol program located in the library, user.dev.cobol, is compiled by a job stored in your JCL library, user.dev.jcl. This job produces a binary file called a load module, which is stored in the load library, namely user.dev.load. Let's now look at how we actually compile a program on z/OS. Compilation is done by executing a job that is available in your JCL library. The job is named cobcomp. Let's take a closer look at this job. We can enable syntax highlighting by typing the command hi_jcl. Here's what a job looks like. In JCL, each line starts with two slashes. The first line defines the job's header, which includes its name. Below that are the steps that execute programs. In this JCL, there is only one step, called CL, which runs the Cobol compilation procedure cobcl. In this step, we need to specify where our Cobol program is located. So, on line 9, we indicate the library containing our Cobol programs, user.dev.cobol, and on line 10, we specify the member corresponding to our program, hello. On line 8, we indicate the load library where the compiled binary will be generated. I won't go further into how JCL works for now, since we'll cover it in detail in a dedicated section. To execute the JCL, type the command sub, which stands for submit. Press enter to refresh the screen, and you should see a return code of 0, which means the job completed successfully without errors. You can check the load library, and you should find the load module for your program. We will now use this load module to run our program. Once the program is compiled, we can run it. To do so, we need to submit a job again. The execution flow is as follows. The execution is handled by a job. This job uses the compiled program's load module to run the program. It may also use input data, which we call the program's input. This can include files or parameters. After execution, the program can produce output, such as creating new files. In our case, since this is our first program, there is no input, and the only output is the display of a message in the job's output report. The execution JCL we'll use for this example is the cobrun job. It looks similar to the compilation job, starting with the initial job identification lines. It consists of a single step, step 01, which runs a program. The name of the program is specified in the PGM parameter, so we write hello there. On line 5, we indicate where the load module for this program is located. We then use the sub command to submit the job. When a program is run, it returns a return code that indicates how the execution ended, and the system automatically assigns a job ID to our job. In this case, the job returns a code 0, which means the program executed successfully. We will now view the execution report of our job. To do this, we'll use a utility called SDSF, which stands for Spool Search and Display Facility. SDSF gathers the results of all jobs that have run since the system was started. We access it using option S. There are several available menus. The one we're interested in is ST for Status of Jobs. Here we get a list of all jobs that are either completed or currently running. The columns are as follows. First, we have NP, which is used to type commands for a specific job. Then we have job name, which displays the name of the job. Job ID is the identifier automatically assigned to each job that runs. If I run the same job multiple times, the system will assign a new ID each time. Owner is the user or resource that submitted the job. To display only the job submitted by our user, we use the command owner followed by the user ID, so in my case I write owner user 01. The Q column shows the current status of the job. Execution means the job is still running. Jobs in execution appear in white. If not, the job has completed. The white line with a job ID starting with TSU corresponds to our current TSO session. We can find the Cob run job that we just executed. To view the contents of the job, we type a question mark in the command column next to it. We usually see 3 lines for the JCL itself, followed by 1 line for the output of each step. In our case, we only have 1 step. Step 01, and an output section called sysout, which is the standard system output. The sysout line for step 01 contains the system output of our hello program. This is where all display statements from the program appear. To view it, we type S and we can see our message, hello world. We can also view the compilation reports since compiling also runs a job. For example, I will recompile the hello program. I go back into SDSF and can see the job appear. I can then open its report. This will be helpful when we need to debug our code and understand compilation errors. Thanks to this small Hello World program, we've seen how to compile and execute a program, and we now know how to check the results using SDSF. We're now ready to deepen our understanding of Cobol program development. We're starting a new section where we will now explore the fundamental concepts you need to know to develop in Cobol. And to begin, we'll take a closer look at the structure of a line of code in Cobol, particularly the concept of margins. In Cobol, each line of code follows a strict format, inherited from the days of punched cards. A line is divided into columns with well-defined margins. We've seen that in a Cobol program, each line is divided as follows. Columns 1 to 6 were historically used to indicate line numbers, but nowadays you can write whatever you want there. Column 7 is used as a line indicator. For example, an asterisk indicates a comment line, which is ignored by the compiler. Columns 8 to 72 are the actual Cobol code area, and columns 73 to 80 were used for the system sequence numbers in the past, but are no longer used. Within the Cobol code area, we distinguish between margin A and margin B. Margin A is the area between columns 8 and 11. It is used for the following elements, which we'll explore further in the course: divisions, sections, and paragraphs, and for level 0, 1, and 77 variables in the data division. This means that the first letter of these elements must be written starting in margin A. Keep in mind that margin A is where the structural elements of your program are written. Next, we have margin B, which spans columns 12 to 72. This is where the Cobol instructions are written. That's why in the Hello World program, the division were written in column 8 and the display and stop run statements were written in column 12. Cobol is a hierarchical language. This means that a program is made up of elements which themselves contain other elements. The highest level element is the division. Divisions contain sections. Sections may contain paragraphs, and finally, paragraphs contain instructions. As we have seen previously, a Cobol program is divided into four main divisions: the identification division, the environment division, the data division, the procedure division. A division starts with its name written in margin A, and it ends when the next division begins. Divisions in a program can be further broken down into sections. With the exception of the procedure division, these sections are predefined. For example, the working variables of a program must be declared in the working storage section of the data division. In the procedure division, it is the developer who defines the names of the sections. We will explore all the predefined sections throughout this course. Sections are optional in the procedure division, but they help organize the program more clearly. To declare a section, you write its name in margin A, followed by the word section and a period. For example, this is how you declare the working storage section. This is the section where we will declare the working variables used in the program. Sections can themselves be broken down into paragraphs. Paragraphs are developer-defined and help structure the program. They usually represent a specific action that contains a sequence of instructions. A paragraph may also call other paragraphs. For example, in the hello program, we write the paragraph say hello. This paragraph contains only the display instruction. The end of the paragraph is marked by a period. We will explore paragraphs in more detail later in the course. Finally, at the lowest level of the hierarchy, we find instructions. An instruction is a line or set of lines of code that performs a specific action. It is the basic unit of execution in a Cobol program. In the Hello World program, we saw the display instruction, which outputs a message to the system. In this lesson, we will take a closer look at the identification division. Every Cobol program begins with the identification division. It serves to identify the program and plays a key role in documenting it. In a production environment with hundreds or even thousands of Cobol programs, the identification division makes it easier to quickly determine what the program is used for, who wrote it, and in what context it is used. This helps with both corrective and evolutionary maintenance. Here is how the identification division is written. It contains the mandatory program ID paragraph, where the name of the program is specified. It may also include optional paragraphs such as date written and date compiled. Program ID must be written first, while the optional paragraphs can appear in any order. The program name can be up to 8 characters long. The optional paragraphs are the following: author, which is the name of the person who wrote the program; date written, which represents the date the program was written; date compiled is the date the program was compiled. Then we have installation, which is the name of the company where the program is used. And finally, we have security, which is the confidentiality level of the program. These clauses are not mandatory, but they provide better documentation, which is especially valuable in large-scale environments like banking or industry where Cobol is widely used. Comments are lines that are ignored during program execution. They are used to explain code for the developer or a future reader, document an important section, temporarily disable a line of code. To insert a comment in Cobol, simply place an asterisk in column 7. For example, in the Hello program, I'm going to add a comment in the identification division to describe what the program does. So I insert a new line, put an asterisk in column 7, and write, "This program displays Hello World." You can also comment out a line of code. For example, I'll duplicate the display statement, comment out the original line, and change the message to "Hello there." I then recompile the program. Now, if I run it and access the report in SDSF, the message "Hello there" is displayed, and we can see that the commented out line was not executed. In this lesson, we'll learn how to analyze compilation errors and how to fix them. It's very important that you know how to do this because you'll almost certainly make mistakes while following the upcoming lessons. I'll deliberately introduce an error into the hello program. For example, I'll write the asterisk in column 8 instead of column 7, and I'll forget to put a space after the display instruction. Let's compile our program. We get a return code 12, which indicates that the program contains severe errors. There are 4 levels of messages that the compilation process can generate. If everything is okay, the compilation returns a code 0. If the compilation generates warnings, it returns a code 4. In this case, we consider the compilation to be successful. A code 8 means errors were detected and the compilation failed. And a code 12 indicates the presence of severe errors and the compilation also failed. Next, we check the compilation job report in SDSF. The compiler outputs a fair amount of information. Use the F8 key to scroll down because the parts we're interested in are located toward the bottom of the report. Here, you'll find a summary of the messages generated by the compilation, along with their severity levels. Informational messages, warnings, errors, and severe errors. My tip to quickly locate these messages is to search for the word severe using the F command. In our case, the compilation has generated 3 messages: a warning, an error, and a severe error. Just above this summary, you'll find the detailed list of messages. On the left, you'll see the line number in question. Then there's an error code. The last letter of that code indicates the severity level. Finally, the actual message is shown. Be careful. In the compilation report, your program listing appears earlier. The line numbers shown in the messages refer to the report version of the program, not your original source file. Here, since we're working with a small program, the line numbers are the same, but this won't be the case when we look at more complex programs. You should always start by fixing the first errors because later ones may be caused by the earlier issues. So, according to the report, we have 2 errors related to line 19. The first error is that the asterisk on line 19 shouldn't be written in area A. Let's fix that by placing the asterisk in column 7 and recompile the program. Now, the compilation returns a code 4, which means it was successful but with warnings. In the report, the warning tells us that on line 20, a space is missing just before the apostrophe, and it even tells us which column the apostrophe is in. At this point, nothing prevents me from running the program. It will work. Now, if I fix the warning by adding a space, the compilation returns a code 0. In this lesson, we will learn how to declare variables. What is a variable? A variable is an element declared in a program to store a value. It associates a name with a value. This value can be of different types. It can either be a character string or a number. This value can change during the execution of the program, hence the name variable. So how to declare a variable? Variables are declared in the data division, which is divided into two sections: the file section and the working storage section. In the file section, we declare the variables that describe the structure of the files. In the working storage section, we declare working variables, that is, the variables we'll use for the program's logic within the procedure division. Let's take the example of a variable named city declared as follows. The structure of a variable is as follows. The first element, 0, 1, indicates the level of the variable. Every variable declaration starts with a level number, which organizes variables hierarchically. Level 0, 1 represents the highest level, and levels can range from 1 to 49. Level 0, 1 must be written in area A of the Cobol program. The second element is the name of the variable. It must follow these naming rules. It must start with a letter. It must not exceed 30 characters. Only letters, digits, and hyphens are allowed. And it must not be the same as a reserved Cobol word, such as division, section, etc. Then we have the picture clause, written as pic. It defines the type of the variable. Pic x is used for alphanumeric values, and pic 9 is used for numeric values. Here, city is a alphanumeric because it uses pic x. Here is another example with the variable number of inhabitants, which is a numeric variable. You'll notice that after pic x or pic 9, we include a number in parentheses. This number defines the size of the variable. This is where Cobol can be a bit more complex than other languages because you must know the size of the variable in advance. So, pic x20 means that city can hold a string of up to 20 characters. And pic 97 means that number of inhabitants can hold a number with up to 7 digits. Of course, the variable may contain a shorter value during execution. There are also other data type notations to declare decimal numbers or packed numbers, but we will cover those more advanced topics later in the course. Then we have the value clause that allows you to initialize the variable. In our example, we initialize the variable city with the value London. The variable city is an alphanumeric variable, so its value must always be enclosed in quotes like hello world. Whereas the variable number of inhabitants is a numeric variable, so its value is not enclosed in quotes. Finally, we end a variable declaration with a period. As the number of variables in a program increases, it becomes much harder to keep things organized. To help with this, we can group variables together. This is known as creating a group of variables. Here we have the group user declared at level 0, 1. Level 0, 1 is the highest in the hierarchy. The lower the level number, the higher the variable sits in the hierarchy. More precisely, we say that user is a group item. A group item contains elementary items, which in this case are user ID, user name, and user age. You can assign any level number to the elementary variables that is greater than the level number of the group item. It's common practice to use multiples of 5, as shown in the example. Elementary variables are typed. They have a picture clause. In contrast, a group variable has no type, since its only purpose is to contain other variables. It is entirely possible to use a group variable in your program's logic. In this example, it allows handling a user as a single entity while still having access to its individual fields. For example, you can display all the data inside user with display user. You can also create subgroups within a group. Here we have defined another group item, username, inside the main group user. It contains two elementary items, user first name and user last name. Typically, we build a hierarchy where the main group variable is declared at level 0, 1, and we increment levels by 5 for each step down in the hierarchy. Incrementing by 5 isn't mandatory, but it is widely used in practice. It gives you room to add intermediate levels later if needed. I also strongly recommend that you indent your variables according to their position in the group hierarchy. This makes the structure of the group much easier to read and understand. Now let's start focusing on the logic of the program by writing instructions. These instructions are written in the procedure division, starting from margin B. The first instruction we'll look at is display, which we've already briefly encountered when writing the Hello World program. The display statement is used to output messages to the sysout. This command is often used to show summary messages at the end of a program, or to debug the program. In long programs, it's common to insert display statements to help understand how the program executed, or to analyze how a variable was assigned a value at a certain point. The syntax is simple. You write the keyword display, followed by the data you want to output. For example, to display a string, we write display followed by the string. This will output hello world to sysout. To display a number, it's just the same. We write display followed by the number. You can also display a variable, for example, display city. This will print the value contained in the city variable. After compiling and running the program, go into SDSF to check the output. You should see Hello World, 1000 and London, which is the initial value of the city variable. It's also possible to display multiple pieces of data in a single display statement. For instance, display city has number of inhabitants and people. This will display London has 1 million people. You just need to separate each element with the space. Let's recompile and rerun the program to verify the result. The next instruction we will look at is the move statement. Move is used to assign a value to a variable. Let's take a look at an example to understand the syntax. Here's how it works. You write move followed by a value or variable, then use the keyword to specify the destination variable. In this example, the city variable, which was initially set to London, will now contain Paris. The move statement replaces the original value of the variable with the new one. This works the same way with numbers. We can write move 1000 to number of inhabitants. After this line, number of inhabitants will hold the value 1000. Now, if we recompile and execute the program, we see that we display Paris has 1,000 people. You can also move the value from one variable to another. Let's say we declare a new variable city2 and initialize it with Berlin. Then we write move city 2 to city. After recompiling and running the program again, the output is Berlin has 1,000 people. In this video, I invite you to complete an exercise to put into practice what we've learned so far. The goal of the exercise is to write a Cobol program that follows these rules. First, create a new Cobol program named cobx01. Then declare a group variable called full name, composed of the alphanumeric variables first name and last name. Use the move instruction to assign values to first name and last name. And finally, display the full name variable in the sysout. I recommend pausing the video at this point and doing the exercise on your own. Here's my solution. First, we create the new member, cobx01, in our Cobol program library. We start by writing the identification division. We specify the program ID clause with the name of our program. I also add a comment block to describe what the program does. Next, we write the data division. Our variables will be declared in the working storage section, since they are working variables. I declare the group variable full name at level 01. This group variable is composed of the alphanumeric variables first name and last name, which I define at level 05. We can now handle the logic of the program in the procedure division. I assign the value David to the variable first name using the move instruction. Then, I assign Lynch to the variable last name. Finally, I use the display instruction to display the variable full name. At the end, I write the stop run command to terminate the program. Now let's compile and run the program. In the compilation JCL, don't forget to update the member name to match our program. And we must do the same in the execution job. We get the following result. In my case, the output doesn't look great because the first name and last name are stuck together. To fix this, I will add a delimiter variable called WSDelim and initialize it with a space like this. After recompiling, the output is correctly formatted. As you run more and more jobs, the list of output reports in SDSF will grow to the point where you'll need to purge some of them. To delete a report in SDSF, use the P command in front of a job in the NP column. A confirmation pop-up will appear. Press Enter to confirm the deletion. To speed things up, you can perform a multiple deletion. To do this, type /P in front of the first job to delete, and / in front of the last job. Then confirm the deletion. In this lesson, we'll look at another way to assign values to variables using the accept statement. We've already seen that sysout is the standard output of the program. Well, there is also sysin, which is the standard input. Sysin allows you to pass data to the program via the execution JCL. It's written as follows. You have the sysin keyword in the header. Then you write the data to be passed just below. For example, we'll write the message, "Hello World." You end the sysin section with a slash and an asterisk. In a Cobol program, the accept statement allows you to retrieve the input from sysin and store it in a variable. The variable used must be large enough to hold the contents of the sysin. We define the variable WSData to be used for this purpose. And in the procedure division, we write accept followed by WSData. Then we display the content of WSData. After compiling and running the program, we see that we successfully retrieved the content from sysin. An accept statement retrieves the content of one line from sysin. If there are multiple lines in sysin, then you must write as many accept statements as there are lines. The accept instruction is often used to retrieve program execution parameters such as date. In the previous exercise, we defined the WSDelim variable as a separator within the group variable full name. This is acceptable here because we only have one delimiter. But what if we have multiple fields that we want to separate, like in a CSV file? We're not going to create as many variables as there are delimiters, right? Well, in Cobol, we have the keyword filler that can be used for this type of situation. Filler is used in data structure to reserve memory space without assigning a name to the field. This is especially useful for ignoring unnecessary data, creating visual or logical spacing in a structure, or ensuring the exact size of a structure. We'll actually see that last point more clearly when we work with files. To declare a filler, we use the same syntax as for a regular variable with a level number, a pick clause, and a value clause. In our example, we can therefore replace our delimiters with filler like this. The only limitation of filler is that it cannot be used in instructions because these fields have no name. When declaring variables, it is essential to initialize them to avoid unexpected behavior. It's good practice to initialize alphanumeric variables with spaces and numeric variables with zeros. We've seen that the value clause allows assigning an initial value to a variable at the time of declaration. But suppose we have a multi-character alphanumeric variable. Are we really going to manually count how many spaces to put in the value clause? Fortunately, Cobol provides keywords to quickly initialize variables. To fully initialize a variable with spaces, we use the keyword space. And to initialize a variable with zeros, we use the keyword zero. In SDSF, we can see that the alphanumeric variable is filled with spaces and the numeric variable with zeros. It is also entirely possible to initialize variables during the program's execution. For that, we use the initialize statement. Initialize provides dynamic initialization. That is, this instruction sets alphanumeric variables to spaces and numeric variables to zeros. Let's verify this. I remove the value clauses and write in the procedure division, initialize, followed by the name of the variable to initialize. In SDSF, we can see that the alphanumeric variable is filled with spaces and the numeric variable with zeros. Initialize can also be used directly on a group variable. In that case, the elementary variables inside the group will also be initialized according to their type. To demonstrate this, I declare a group variable that includes an alphanumeric variable and a numeric variable. Then I use initialize on the group variable. Since Cobol is widely used in banking applications, you will inevitably need to perform calculations. So let's look at the instructions that allow us to perform arithmetic operations. The basic operations are addition, subtraction, multiplication, and division. To begin, we will declare three numeric variables in our hello program, num1 and num2, which are defined with 2 digits. We initialize num1 to 5 and num2 to 10. And we declare the variable result, which is defined with 3 digits and initialized to 0. The first operation we'll look at is addition, using the add keyword. With add, you can increment the value of a variable using another variable. For example, we'll add num1 to result. To do that, we write add number 1 to result. Then we display the value of result using display. At this point, result should be equal to 5. We can then add num2 to result. And again, we display the result variable. At this stage, we expect result to be 15. After compiling and running the hello program, we get the expected result. It is also possible to write add num1 to num2, giving result. In this case, the value of num2 is not modified. and the result is stored in result. Let's display all three variables and verify this. In SDSF, we see that num1 and num2 have kept their initial values, and result is indeed the sum of num1 and num2. Finally, it's also possible to use numbers directly in the addition. For example, we can increment the result variable by 1 by writing add 1 to result. The next operation we'll look at is subtraction, which is done using the subtract instruction. To illustrate subtraction, we're going to subtract num1 from num2. For that, we write subtract num1 from num2. We expect that the value of num1 remains unchanged, and num2 should now be equal to 5. After recompiling and running the program, we get the expected result. As with addition, it's also possible to store the result in another variable using the giving keyword. For example, if we write subtract num1 from num2, giving result, the values of num1 and num2 remain unchanged, and the result is stored in result. Finally, we can also perform a subtraction directly with numbers. For instance, we can write subtract 1 from num2, giving result, and we get the result variable now equal to 9. In this lesson, we're going to look at the multiply instruction, which, as you might expect, allows us to perform multiplications. We're going to multiply the variables num1 and num2. To do this, we write multiply num1 by num2. In this case, the product is stored in the variable num2. We can also store the result in another variable using the giving keyword, just like we did with the other operations. And we can use numbers directly as well. For example, multiply 2 by 10. For all calculations, make sure that the variables you use are large enough to hold the result. Let me show you an example. If I multiply 100 by 100 and store the product in the variable result, we won't get any error at compile or runtime. However, result will display 0, which corresponds to the last 3 digits of 10,000, because result is defined with only 3 digits. If I define result with 5 digits instead, then the result is displayed correctly, so be careful with this. In this lesson, we'll look at the last arithmetic operation, division. In Cobol, we use the divide instruction. In our example, to divide num2 by num1, we write divide num1 into num2. In this case, the result is stored in the num2 variable. We can also store the result in another variable using the giving keyword. Finally, it can be useful to retrieve the remainder of a division. To do this, we use the remainder option, and we declare a variable num3 to store the remainder. I modify the value of num2 so that the division produces a remainder. With the remainder option, the quotient is stored in the result variable, and the remainder is stored in the num3 variable. The four arithmetic operations we've just seen are the foundation for performing calculations in Cobol. However, it will often be necessary to combine these operations to perform more complex calculations. For that, we have the compute instruction. The compute instruction is written as follows. You write compute, followed by the variable where the result will be stored, then an equal sign, and finally the mathematical expression. Let's see how this works in practice. To perform an addition, for example, you can write compute result equals num1 plus num2. To perform a subtraction, you use the minus sign. To multiply, you use an asterisk. And to divide, you use a slash. You can also combine operations and use parentheses to apply priority, just like in mathematics. Let's verify our different calculations. Num1 is 5 and num2 is 10. The sum of these two numbers is 15. The difference is 5, the product is 50, and the quotient is 2. Finally, num1 plus 5, then multiplied by 10 equals 100. In this new section, we're going to see how to structure the logic of our program using control structures. We'll start with conditional structures using the if statement. The if statement allows you to execute one or more instructions only if a condition is true. Here's the syntax of the if statement. You write if followed by a condition. This condition is followed by one or more instructions to execute. And you end the if block with end if. The instructions inside the if block are executed only if the specified condition is true. Now, let's see how to write a condition in Cobol. A condition is a logical expression that can be either true or false. It is made up of variables and comparison operators. For example, age is greater than 18 is a condition. It is true if the variable age is greater than 18. It is false otherwise. If I initialize the variable age to 50, then the condition is true and the message adult will be displayed. If I now set age to 10, then the condition is false and the message is not displayed. There are, of course, other comparison operators. We can test for equality using the equal sign, strictly less than, greater than, or equal to, and less than, or equal to. In our example, we are comparing a variable to a number, but we can also compare it to a string or another variable. It is also possible to test for inequality using the not keyword. Finally, it is possible to combine multiple conditions using the and or operators. With AND, all conditions must be true for the overall result to be true. For example, age is greater than 18 and country equals USA. In this case, the display instruction is executed only if both conditions are true. With OR, only one condition needs to be true for the overall result to be true. So in our example, if age is greater than 18 and country is equal to Spain, the display instruction is executed. It is also possible to write an else clause to execute instructions when the condition is false. The else is placed right after the first block of instructions. In our example, since the condition is false, the message "not adult" will be displayed. Lastly, it is also possible to nest multiple if statements. A nested if means placing an if inside another if. This allows you to test a condition only if another condition is already true. I recommend properly indenting the code as I've done to improve readability and easily understand where each if block starts and ends. Let's now move on to an exercise to practice the if instruction. For this, we're going to write the COBX02 program, which determines a price based on a person's situation. A person is eligible for the reduced price if one of the following conditions is met. They are under 12 years old. They are 65 or older. They are between 18 and 25 years old inclusive and are a student. We'll declare a numeric variable called age and an alphanumeric variable, category, which will indicate whether the person is a student or not. Here are some examples of expected results. If the reduced rate applies, then display the message reduced price. Otherwise, display full price. I, of course, recommend pausing the video and trying to do the exercise on your own. Here is my solution. First, we'll create the COBX02 program. This time, we won't create it from scratch, but by copying the COBX01 program that we had created earlier. To do that, we type the command C in front of the COBX01 member. On the next screen that appears, we need to specify the library where we want to copy the member. So, in the name field, we enter our Cobol program library, user.dev.cobol. The name must be enclosed in quotes. Then, in the new member name field, we enter the new program name, COBX02. We are informed that the copy was successful. Next, type the ref command to refresh the screen and edit the COBX02 program. I start by changing the program name in the identification division and updating the comment to reflect the program's purpose. I clean up the working storage section by deleting all the existing variables. I declare the variable age as pick9 of 2 and initialize it to 0. Then I declare the variable category as pick_x of 20 and initialize it with spaces. I delete all instructions from the procedure division. To begin, I assign values to age and category using the move instruction and then display them in sizeout. Now, to determine whether a reduced price applies, we'll use the if instruction. We apply the reduced rate if at least one of the following conditions is true. The first condition is if the person is under 12. The second condition is if the person is 65 or older. Since only one condition needs to be true for a reduced price, I link these conditions using the OR operator. The third condition is if the person is between 18 and 25 inclusive and is a student. Since all parts of the third condition must be true, I connect them using the AND operator. Finally, I use parentheses to clearly group the third condition. If any of these conditions are met, I display the message reduced price. Otherwise, I display the message full price using the else clause. I'll also show you a few test cases after compiling this program. In this lesson, we will look at another control structure, the evaluate instruction. But before diving into the explanation, let's take a look at a sample program where a series of if instructions is coded. In this program, we have a sequence of if statements that display a person's life stage based on their age. However, the issue with this code is that it's costly in terms of execution, because for each person, every if condition is tested. For example, in the case of a baby, the first test will be true, but the remaining conditions will still be evaluated unnecessarily. To optimize this code, we can rewrite it using else if statements like this. The if blocks are nested inside one another. This makes the code more efficient, since, for example, if we are dealing with a child, the execution will stop at the corresponding block and then move on to the rest of the program without testing the other conditions. However, when we have many cases to test like this, such cascading structures are not recommended because they are hard to maintain and not very readable. This is exactly where the evaluate instruction becomes useful. Using evaluate, the equivalent of our example would be the following. To write an evaluate block, we begin with the word evaluate, followed by true. Then, inside the evaluate block, we write when clauses that represent the various possible cases. It is in these when clauses that we write our conditions. Each when clause contains a block of instructions that will be executed if the associated condition is true. Finally, there is a when other clause, which is optional but highly recommended, as it allows us to handle all the unexpected or unmatched cases. We end the evaluate block with end evaluate. Be careful in an evaluate statement, only one when clause is executed. For example, if I write a when clause with age lower than 1 and age is 0, both of the first when conditions may be true, but only the first one will be executed, and the execution will exit the evaluate block. It's also possible to evaluate a variable directly. In our example, to test a range of values, we use the keyword through. The numbers specified in a through range are inclusive. By writing our logic using evaluate, we end up with code that is more optimized and much more readable. Let's do a quick exercise to practice the evaluate statement. Let's take the previous exercise where we coded the COB X02 program and modify it to use evaluate instead of the if statement. To do this, we will create the COB X03 program based on COB X03. Here is the solution. You should have arrived at the following evaluate statement. However, I'd like to suggest a small optimization. We can see that for the first 3 when clauses, the same instruction is executed and repeated. In this case, it is possible to improve the code by combining the when clauses as follows. The behavior remains exactly the same. In this lesson, we're going to look at another type of control structure, loops. Loops allow a set of instructions to be repeated a certain number of times or until a condition is met. Each pass through a loop is called an iteration. To create a loop in Cobol, we use the perform statement. There are 3 main types of loops. Loops with a fixed number of iterations. Conditional loops, meaning they run until a condition is true. And loops with a control variable. Let's start with loops that run a fixed number of times. This form repeats a block of code a set number of times. The syntax is as follows. You write perform, followed by a number, then the word times, and you end the loop with end perform. For example, let's write a loop that repeats 5 times. Inside the loop, we write the instructions to execute. In our case, we'll display a variable I, which will correspond to the current iteration number. We'll increment I by 1 at the end of each iteration. Here's the result. We can see that the loop executed 5 times and that the variable was incremented on each pass. The second form of loop is conditional loops. This loop will execute as long as a condition is false. The syntax is perform until, followed by the condition, for example, I is greater than 5. Then we write the instructions to execute and close the loop with end perform. In this example, we go through the loop 6 times. When the variable I reaches 6, the condition becomes true and we exit the loop. With this type of loop, be careful not to create an infinite loop. For example, if we forget to increment the variable I at each iteration, the condition will never become true. I configure the execution job with the time parameter so that it automatically fails if the process takes more than 5 seconds. When executed, we will get an S322 ABN code, indicating that the program took too long to complete. In SDSF, we'll see that the report displays thousands of lines and ends with the code S322. Finally, the third form is the loop with a control variable. This loop automatically increments a variable at each iteration and stops the loop when the condition becomes true. We write it like this: perform varying, followed by the name of the variable. Then we specify the initial value of the variable using the from clause. Next, we specify the amount by which to increment the variable using the by clause. Finally, we provide the condition to exit the loop. For example, we'll initialize the variable I to 1, increment it by 1 on each iteration, and stop the loop when I is greater than 5. We'll simply display I during each iteration. Here is the result. We can see that the variable I was initialized to 1, and then the loop executed 5 times, and it stopped when the condition was true, meaning I was greater than 5. In this section, we're going to focus on the use of the period in a Cobol program. You've probably noticed that I placed periods at specific places in the program. For example, after the names of the divisions, after variable declarations, and after the stop run instruction. But interestingly, I didn't place any at the end of other instructions. In Cobol, it's perfectly valid to put a period at the end of an instruction. However, it's not mandatory, and I recommend not using them. Why? Because the period acts as a block terminator. Let's look at an example to better understand. In the procedure division, we write two instructions. If I put a period at the end of these instructions, the program will still work fine. Now let's wrap these instructions in an if block. In an if, evaluate, or perform block, a period indicates the end of the block. It's called a scope terminator. So if I leave the end if, I'll get a compilation error, because the if block has already been closed by the period. If I remove the end if, the code compiles and we get the following result. You'll notice that the instruction display 100 was executed, even though the condition was false. That's because the period after display hello world ended the if block. So this second instruction is outside the if. You can see how this could hurt readability. To include both instructions in the if block, you either remove the period after the first instruction, or you remove all periods and use end if. This means that it's possible to mix instructions with periods and instructions without. It works, but for the sake of consistency, I recommend not placing periods at the end of regular instructions. However, a period is required after the stop run instruction, as it marks the end of the program. A period is also required at the end of paragraphs and sections. We'll see those structures in an upcoming video. So to summarize, use a period after the names of declarative structures like divisions and sections, after variable declarations, and after the stop run instruction. In this lesson, we will look at the concept of paragraph. Paragraph is a structure that helps organize the code inside the procedure division of a Cobol program. It allows you to group together instructions and improve the readability of the code. Here's how to define a paragraph. For example, we'll create a paragraph called initVar, whose purpose is to initialize variables at the beginning of the program. A paragraph is declared in margin A by specifying its name followed by a period. Then in margin B, we write the instructions that will be part of the paragraph. We end the paragraph by writing a period. Next, we need to call this paragraph to execute it. To do that, we use the perform instruction followed by the paragraph's name. When the perform is executed, the program jumps to the paragraph, runs its instructions, and when it reaches the terminating period, it returns to continue executing after the perform. The advantage of a paragraph is that it is reusable and can be called multiple times. For example, we might define a paragraph called append that is used in case of an error. It would display an error message and stop the program. This paragraph could be called from various places in the program. There's another way to write a paragraph. You can give the paragraph an ending name, like this, and follow that name with the exit instruction. When using this form, we call the paragraph using the through keyword with the ending name. This style is commonly found in Cobol programs. The difference in execution is that the paragraph ends at the exit instruction before continuing with the instruction that follows the perform. In this lesson, we're going to talk about another element that helps organize the structure of a program: sections. We've seen that paragraphs are used to group instructions. Well, sections are used to group paragraphs. Let's see how this works in practice. In the procedure division, we have the paragraphs open files and init var. We can group these paragraphs into a section called init like this. You write the name of the section in area A, followed by the keywords section and a period. Then you place your paragraphs under it. A section ends either when another section starts or when the end of the program is reached. To call a section, we use the same syntax as for paragraphs: the perform instruction followed by the name of the section. A section can also contain instructions directly. For example, I define the sections finish and main that contain display instructions. Then I call them using a perform. We get the following output. So it's perfectly valid to write a program using only sections, only paragraphs, or a combination of both. It depends on your personal preference as a developer or the standards of the project you're working on. Personally, I prefer coding using only paragraphs, so I'll continue in that style for the rest of the course. In this lesson, we'll focus on level 88 variables. This type of variable is called a condition name. A condition name is simply a name that represents a condition. For example, the variable is adult could represent the condition age is greater than 18. Let's look at an example right away to understand how this type of variable works and why it's useful. To declare a condition name, you first declare a variable. For instance, let's define a variable age that stores a person's age. Then, within that variable, we declare level 88 variables that represent different age categories. For example, we can define the variable isBaby, and in the value clause, we specify the values that will make isBaby true, for instance, 0, 1, and 2. In the clause, you can specify one or more values, and you must separate the different values with a space. It's also possible to define a range of values using the through keyword, like this. You can then define all age categories like so. This means that if age is between 0 and 2, then isBaby will be true, and all other age categories will be false. In the procedure division, you can then use condition names and instructions such as if, evaluate, and perform until. For example, we set age to 2, then we can write if isBaby, followed by instructions specific to babies. In this example, isBaby is equivalent to the condition age is lower or equal to 2. It's also possible to directly set a condition name to true using the set instruction. For example, to activate isAdult, you can write set isAdult to true. The set instruction in this case will assign the value defined in the value clause of isAdult to the variable age. If a range of values is defined, the first value in the clause will be used, in our case 18. However, be careful. It is entirely possible for two condition names to be true at the same time if they share common values. For example, imagine the variable months. If we move 3 to months or set isMarch to true, then both isMarch and isFirst trimester will be true. By using a condition name, you simplify both code readability and maintainability. Imagine if tomorrow you decide that a person is still considered a baby at age 3 instead of 2. Without condition names, you'd have to manually update every if condition in the program to reflect this change. But with a condition name, you only need to update the value clause in the variable declaration. I suggest we do an exercise that will help you put into practice the concepts we've covered so far. The goal of this exercise is to create a Cobol program that calculates the sum of the integers from 1 to n, with n being a number entered by the user at runtime. The program must follow the following rules. First, retrieve the user input. This input corresponds to the number n. The entered number must be less than 50. Implement a check to verify this condition. If this rule is not respected, display the following report in sysout. If the input is OK, then calculate the sum of integers from 1 to n. Finally, display the following report in sysout. As usual, I invite you to pause the video and try to complete the exercise on your own. Here's my solution. In the working storage section, we declare the necessary variables. WS input contains the integer n entered in syson. WSI is the counter used for the loop from 1 to n. WS sum will store the calculated sum. WS message is the message to display in case of an error. And status switch holds the condition names OK and KO. These will help determine whether the input is valid. The program then runs in 4 steps. The first step is initializing the variables in the initVar paragraph. We initialize the sum WSSum and the error message. Then we initialize the counter WSI to 1. We also set the status switch to OK. Finally, we read the user input using accept WS input. The second step is input validation. We check whether the number entered is greater than 49. If it is, then we set KO to true and store the appropriate error message in WS message. If the input is valid, then OK will be true, and we move on to the third step, which is the sum calculation using a perform until. On each iteration, the loop adds WSI to the sum until WSI is greater than WS input. In this way, we correctly calculate the sum of integers from 1 to the entered number. Finally, the last step is to display the report. This report shows the execution status, either OK or KO, as well as the input value. If the processing is OK, we display the sum. Otherwise, we display the error message. Now, if I run the program and enter 05 in the SISN, we correctly get 15. And if I enter 60, we correctly get the error message. Please note that since WS input is defined with 2 digits, this format must be respected in the SISN by writing numbers with 2 digits. For example, if I just enter 4 in the first position, we don't get 10 but 820, because in this case 4 is interpreted as 40.